The solver add-in allows us, allows a scientist to find parameters of a model that best fit experimental data. And so what I wanted to do today is show how we can use that tool in modeling experimental data that one might have collected in an experiment. In order to do this, we are going to need to perform the following steps. First, we need to ensure that the solver is actually installed in Excel. Then we import the data, design a particular, specific spreadsheet, and then we'll identify some starting points, a good starting point for our model. First, to make sure that the solver is installed, we're going to go up to the Excel file and look under options. And we see under options here, under the add-ins, I've already added in the solver add-in. However, if we need to manage the add-ins, you would be able to click on this checkbox here to make sure that it is installed. This is true for the later versions of Microsoft Excel. If you just Google Excel Solver add-in, for example, add-in Mac or add-in 2007, 2016, then you'll find the instructions for your particular version of Excel. But essentially, Word PC versions after 2007 and Mac versions after 2011 all have the solver available, just not installed by default. Okay, I'm going to use the Vendee equation, which is this equation right here, which is used to predict the efficiency of a chromatographic process and shows how this process is influenced by the flow rate of the mobile phase. So it's standard analysis that we do in analytic chemistry. The area in the light gray is what is experimental data that I've collected, say flow rate, and I have obtained experimental heights of theoretical plates. And when we plot this data, we see that it starts off high, reaches some sort of minimum, and then starts to increase. In this particular experiment, you're trying to find the flow rate that gives the smallest theoretical plate size, because that's what's going to give you the best separation. The Vendee equation has three different components to it, and these A, B, and C parameters are the parameters that we would want to actually solve for. Ux is the flow rate, H is the Y is the value that we're actually trying to that we've measured. And so the way I've set up this this spreadsheet, we start off with our experimental data. So these I've typed in. The column C is the model, and the model is essentially the Vendee equation. So I've kept constants for A, B, and C. I'm not going to go over how we would actually plug in the model in this particular tutorial. What's important to this analysis is that we compare the experimental with the model, and the way we're going to do that is by taking the difference between the two and then square it. So we're ultimately going to take the sum of the square of the differences. And the technique that we're doing is technically called minimizing the sum of the squares of the residuals, which is essentially comparing the experimental and the model values and trying to make sure that these two values are as close together as possible. So in column D, I've got the difference and I've squared them to keep all these values positive, and then over here in H4 I have just added up all of these values. So this is the sum of the squares of the differences. When this value, if this value is 0, that would mean that there's a perfect fit between the experiment and the model. By setting A, B, and C to 0 right now, we see the black line shows that this is an absolutely terrible fit, which obviously is not too surprising, but let's start there. If we take a closer look at the Vendee equation, we see that that A corresponds to a constant, C is a linear term, and B is an inverse term. So if we just changed A to some value, we would see that it just increases the height a little bit. And then if we change C a little bit, we see that it adjusts the slope. And so we can start playing with these just a little bit to get an idea of where we would get good starting values. We don't need to spend a lot of time getting really close, but we want to get something that predicts somewhat of the shape, like so. So let's go with this, where we see that it does have roughly the shape, but the residuals is still fairly high. So let's see if we can minimize that. I'm going to go into the Data tool, select Solver, and up comes the solver. The objective is going to deal with H4, and H4 is the sum of the squares, the differences. I want to create a minimum. I want to get that minimum value as small as possible, and I'm going to do that by changing cells H1 through H3, so the A, B, and the C. I could add some constraints. For example, I could tell that these values can't be below 0, but I'm going to leave that for this particular case because it is not necessary. I click Solve, and it asks if we want to keep this value or not. I'm going to hit OK, and notice a couple things happened here. It changed these values. The sum of the squares of residuals is very small, and the plot looks nice and clean. So it looks like we've actually got a good, decent fit here. And so this is a very quick and easy way to see what parameters in your model best fit your experimental data.